On November 10th, 2025, astronomers watching the sky captured something remarkable through telescopes pointed toward the eastern horizon. High above Italy, a computer-controlled telescope followed a moving speck of light that was streaming back into the depths of space after its close pass near the Sun. This visitor, known as 3I/Atlas, showed a long glowing tail stretching across the darkness. But what made this night special was not just the tail itself. Scientists had been watching this object shed dust in a rhythm, a pattern tied to how fast it spins as it tumbles through space. Every 16 hours and 10 minutes, the cosmic visitor completes one full rotation, and with each turn, it releases more dust into the void. This is not just any space rock drifting past Earth. 3I/Atlas is an interstellar comet, meaning it came from beyond our solar system, from the space between the stars. It is only the third visitor from another star system that we have ever spotted passing through our neighborhood. Think about that for a moment. In all of human history, in all the thousands of years we have looked up at the night sky, we have only confirmed 3 objects that came to visit us from the galaxy beyond. 3I/Atlas arrived in early summer of 2025, and scientists immediately pointed every available telescope toward it, eager to learn its secrets. What they discovered was a cosmic traveler that does not quite fit the usual patterns. It sheds dust in a steady beat, like a cosmic metronome keeping time as it races through our solar system. Let's step back and understand what makes this visitor so special. Where did it come from? What is it made of? Why does it shed dust in such a regular pattern? And what can it teach us about worlds circling distant stars, stars we will never visit in our lifetimes? Stay with me, and we will walk through this cosmic mystery together. We will meet the telescopes that spotted it first, the scientists racing to study it before it vanishes forever, and the handful of other interstellar visitors that came before. We will explore what it means when something spins in space, how comets wake up and start shedding material as they warm in the sunlight, and why this particular visitor might be older than our entire solar system. The story begins on the 1st of July 2025 at an observatory in the mountains of Chile. Picture a telescope sitting in the clear desert air, far from city lights, where the stars blaze overhead in endless numbers. This telescope is part of a system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System. Its job is to scan the sky every night, looking for anything that might be heading toward Earth. The telescope takes pictures of the same patches of sky over and over, comparing each new image to the ones before, searching for anything that has moved or changed. On that July night, the computer noticed something new. A faint dot of light appeared in the images where no dot had been before. The telescope software flagged it immediately and sent an alert to astronomers around the world. Within hours, other telescopes swung toward that same spot in the sky to take a closer look. These follow-up observations revealed something extraordinary. The object was moving fast, incredibly fast, and its path through space was not a gentle curve like the orbits of asteroids and comets, born in our solar system. Instead, it was following what scientists call a hyperbolic trajectory, a path shaped more like an open arc than a closed loop. This shape told astronomers that the object was not trapped by the sun's gravity. It was just passing through, moving so fast that nothing could hold it here. The discovery set off a flurry of excitement. Scientists checked older telescope images to see if anyone had photographed this visitor before without knowing what it was. They found it hiding in pictures going all the way back to mid-May, more than a month before the official discovery. In one set of images, the comet was passing in front of the dense star fields near the centre of our galaxy, which made it hard to pick out against the background of countless stars. It was like trying to spot a single firefly in front of a forest full of Christmas lights. By July 2nd, astronomers had gathered enough observations to give the object its official name, 3I/Atlas. The 3I part means it is the third confirmed interstellar object ever discovered. The word Atlas comes from the telescope system that spotted it first, and the letter I stands for interstellar, marking it as something that came from beyond our solar system's edge. But here is where things got interesting. As more telescopes turned toward 3I/Atlas, scientists started to see details that surprised them. The object was not just a dark rock tumbling through space. It had a coma, a fuzzy cloud of gas and dust surrounding its centre. This coma is the hallmark of a comet. When comets get close to the Sun, the ice on their surface starts to turn directly from solid to gas without melting first, a process called sublimation. It is the same thing that happens when dry ice, which is frozen carbon dioxide, starts to smoke and disappear in warm air. As the ice turns to gas, it carries tiny dust particles with it, creating that fuzzy glow around the comet's core. Telescopes in Hawaii, Arizona, and the Canary Islands all confirmed that 3I/Atlas had this fuzzy appearance. The coma had a reddish colour, which told scientists that the dust being released was rich in organic compounds, complex carbon-based molecules similar to those found in some comets born in our own solar system. By July 21st, the Hubble Space Telescope, orbiting high above Earth's atmosphere, captured incredibly sharp pictures of 3I/Atlas. These images showed something fascinating. The dust cloud around the comet was shaped like a teardrop, with most of the material being released on the side facing the Sun. This teardrop shape held a clue about how the comet was behaving. Most comets we know spin fairly quickly as they tumble through space, causing them to heat up evenly as different parts take turns facing the Sun. But 3I/Atlas seemed to be spinning more slowly, allowing one side to get much hotter than the other. The hot day side was where most of the dust was coming from, streaming away from the surface like smoke from a chimney. Scientists working with telescopes in the Canary Islands measured how bright 3I/Atlas appeared at different times over several nights in early July. They noticed something remarkable. The brightness changed in a regular pattern, getting slightly brighter, and then slightly dimmer, then brighter again. This pattern repeated every 16 hours and 10 minutes, give or take a few minutes. This was the rotation period, the time it took for the comet to spin once around its axis. Imagine the comet is like a chicken roasting on a spit, turning slowly so that each part gets its turn in the heat. Every 16 hours, the same spot on 3I/Atlas comes back around to face the Sun again. But why does the rotation matter? Here is where the perfect beats come in. As the comet spins, the hot side constantly changes. When a fresh patch of surface rotates into sunlight, the ice there starts to warm up and sublimate, releasing dust. As that patch rotates away into shadow, it cools down and the sublimation slows. This creates a rhythm, a pattern to the dust release that matches the spin. The comet is not shedding dust randomly. It is shedding dust in pulses, in beats, timed to its rotation. Now imagine standing far away and watching this happen. You would see puffs of dust lifting off the surface in waves, one wave every time the comet completes a rotation. The dust does not stay near the comet. It drifts away, pushed by the pressure of sunlight and carried along by the gas that is also escaping. Over hours and days, these waves of dust spread out into space, creating streams and patterns in the comet's tail. Scientists studying 3I/Atlas calculated that it was losing somewhere between 6 and 60 kilograms of dust every second, depending on the size of the dust grains. 60 kilograms is about the weight of a large adult person. Imagine a whole person's worth of dust lifting off the comet's surface every single second. Even at the lower estimate of 6 kilograms per second, that is still a tremendous amount of material leaving the comet, and all of this dust release follows the rhythm of that 16-hour rotation. The comet's steady spin creates what scientists call periodic variations, changes that happen over and over in a predictable pattern. These periodic variations show up in measurements of how bright the comet appears, how much dust it is releasing, and even in the shape of the dust cloud around it. The perfect beats are not something the comet decides to do. They are a natural consequence of how heat from the sun interacts with the spinning, icy surface. Let's zoom out now and think about the bigger picture. Where did this cosmic visitor come from, and how did it end up passing through our solar system? To answer that, we need to understand what scientists mean when they say interstellar. Our solar system is like an island in space. This sun sits at the center, and all the planets, asteroids, and comets orbit around it, held in place by the sun's gravity. Everything in our solar system formed together about 4.5 billion years ago from a giant cloud of gas and dust. This sun formed first, and the leftover material swirled around it, eventually clumping together to form the planets and everything else. Interstellar space is the vast emptiness between star systems. It is not truly empty, of course. There is thin gas drifting through it, grains of dust, occasional molecules, and every so often, objects like comets or chunks of rock that were flung out of their home star systems. These objects drift through the galaxy for millions or even billions of years, travelling through the dark until one day, purely by chance, they pass close to another star. 3I/Atlas is one of those wanderers. Scientists have traced its path backward through time, following the mathematics of how gravity and motion work. Their calculations show that 3I/Atlas came from the direction of the constellation Sagittarius, near the center of our galaxy. It has been traveling through interstellar space for a very, very long time. Researchers led by scientists at Harvard University calculated that 3I/Atlas is probably about 4.5 billion years old, roughly the same age as our entire solar system. It likely formed in a disk of gas and dust around another star billions of years ago, when that star was young. Something happened back then, something violent enough to fling this comet out of its birth system and send it flying into the galaxy. Maybe a giant planet migrated inward through that distant planetary system, using its gravity to throw smaller objects like 3I/Atlas out into space. Maybe the comet passed too close to another star that was passing by. Whatever happened, 3I/Atlas escaped its home and began a journey that would last billions of years. For all that time, 3I/Atlas drifted through the galaxy. It probably never came close to another star. It just moved through the dark, spinning slowly, growing colder and colder until it was just a few degrees above the coldest temperature possible, what scientists call absolute zero. Cosmic rays, which are high-energy particles racing through space, constantly struck its surface, breaking apart some of the molecules there. Over millions of years, this radiation damage might have changed the comet's outer layer darkening it and creating some of the complex organic molecules that give it that reddish colour. Then, sometime in 2025, 3I/Atlas happened to pass close enough to our Sun that the Sun's gravity began to pull on it. The comet's path bent slightly, curving it through the inner solar system. As it got closer to the Sun, it started to speed up, pulled along by gravity like a ball rolling down a hill. When scientists discovered it in early July, it was travelling at about 137,000 miles per hour, or if you prefer, about 221,000 kilometers per hour. That is fast enough to cross the entire width of the United States in about 2 minutes. As 3I/Atlas fell closer to the Sun through the summer of 2025, it moved faster and faster. The Sun's heat also started to reach it, warming the frozen surface for the first time in billions of years. This is when the comet woke up. Ice that had been frozen solid since before Earth existed started to sublimate, releasing gas and dust. The coma appeared, and the comet began its rhythmic shedding of material, timed to that 16-hour spin. On October 30th, 2025, 3I/Atlas reached its closest point to the Sun, a moment scientists call perihelion. At that moment, it was about 130 million miles from the Sun, or about 210 million kilometers. To give you a sense of scale, that is just inside the orbit of Mars. Earth was on the opposite side of the Sun at that time, so we could not see the comet directly during its closest approach. But spacecraft orbiting Mars had a front row seat. The European Space Agency has a spacecraft called the ExoMars Trace Gas Orbiter, circling Mars, studying the red planet's thin atmosphere. In early October, mission controllers turned that spacecraft's cameras away from Mars and pointed them at 3I/Atlas. The comet was passing about 29 million kilometers from Mars, close enough for the orbiter's instruments to capture detailed observations. These observations from Mars, combined with observations from Earth, helped scientists nail down the comet's exact path through space with much better accuracy than before. It was like triangulating a position using 2 observation points instead of just 1, which gives you a much more precise answer. At perihelion, 3I/Atlas was moving at its fastest speed during the entire visit, about 153,000 miles per hour, or 246,000 kilometers per hour. Then, as it swung around the Sun and started moving away again, it began to slow down, fighting against the Sun's gravity, pulling it back. But it was moving much too fast for the Sun to capture it. The comet's path remained hyperbolic, an open arc that would carry it back out into interstellar space. After perihelion, 3I/Atlas passed behind the Sun as seen from Earth, which meant we could not observe it for several weeks. During that time, a weather satellite called GOES-19, which usually watches Earth's weather from space, managed to spot the comet even though it was faint and close to the Sun in the sky. By early November, 3I/Atlas emerged from behind the Sun and became visible again in the pre-dawn sky. Astronomers immediately resumed their observations. Pictures taken in mid-November showed that the comet now had a much more obvious tail. This tail was not the dust tail we have been talking about. It was an ion tail, made of electrically charged gas molecules that get pushed away from the Sun by the solar wind. The solar wind is a stream of particles constantly flowing out from the Sun in all directions. When these particles hit the gas around a comet, they push the gas straight away from the Sun, creating a long straight tail that can stretch for millions of kilometers. The ion tail of 3I/Atlas was pointing away from the Sun, stretching at least 0.7 of a degree across the sky, as seen from Earth. That might not sound like much, but in space terms, it represents a tail hundreds of thousands of kilometers long. The tail glowed faintly blue-green, colored by gases like carbon monoxide that emit light at specific colors when they get energized by sunlight. Now let's talk about what 3I/Atlas is made of, because this is where things get really interesting. In August, the James Webb Space Telescope turned its infrared eyes toward the comet. The Webb telescope is humanity's most powerful space telescope right now, capable of seeing light that is invisible to human eyes. It orbits the Sun about 1.5 million kilometers from Earth, far enough that Earth's heat does not interfere with its ultra-sensitive instruments. When Webb looked at 3I/Atlas, it saw chemical fingerprints, patterns in the light that reveal which molecules are present in the comet's coma. The results were surprising. 3I/Atlas has one of the highest ratios of carbon dioxide to water that scientists have ever measured in any comet. For every water molecule in the coma, there were about 8 carbon dioxide molecules. That is very unusual. Most comets in our solar system have much more water than carbon dioxide. Think about comets like Halley's Comet, which visits the inner solar system every 76 years, or any of the dozens of other comets we've studied up close. In those comets, water is the main ingredient, with smaller amounts of other ices mixed in. But 3I/Atlas flips that pattern. Carbon dioxide dominates, with water playing a smaller role. This high carbon dioxide ratio tells scientists something important about where 3I/Atlas formed in its original star system. Carbon dioxide freezes at a higher temperature than water, which means it stays frozen farther from a star where things are warmer. Water only freezes into ice much farther out, where the cold is deep and intense. The fact that 3I/Atlas has so much carbon dioxide suggests it formed in the very outer reaches of its birth system, way out beyond where any planets were orbiting, in a region similar to our own Kuiper Belt or Oort cloud. The Kuiper Belt is a region of our solar system that starts beyond Neptune's orbit and stretches out for billions of kilometers. It is full of icy objects, leftovers from when the solar system formed. The Oort cloud is even farther out, a vast shell of icy objects surrounding our solar system at distances so great that light from the sun takes months to reach them. 3I/Atlas probably formed in a similar region around its home star, then got ejected into interstellar space sometime long ago. Webb also detected other molecules in the comet's coma: water vapor, carbon monoxide, and something called carbonyl sulfide, which is a molecule containing carbon, oxygen, and sulfur. The SPHEREX spacecraft, a telescope that studies how light spreads across the infrared spectrum, also observed 3I/Atlas in August and confirmed the presence of these molecules. Scientists can use these chemical fingerprints to compare 3I/Atlas to comets born in our own solar system, looking for similarities and differences. One of the interesting things scientists found was nickel. Using a huge telescope called the Very Large Telescope in Chile, researchers detected vapor from nickel atoms in the comet's coma. Nickel is a metal, and finding metal vapor around a comet is unusual but not unheard of. As the ice sublimates from the surface, it can drag along tiny grains of dust that contain metals. When sunlight heats these dust grains, some of the metal can evaporate, creating a thin vapor. Nickel vapor has been seen in other comets before, including the previous interstellar comet 2I/Borisov, but it is still a bit mysterious why we see nickel and not other metals that should be present in similar amounts. As summer turned to fall in 2025, telescopes continued tracking 3I/Atlas. Observations from the James Clerk Maxwell Telescope in Hawaii, which detects submillimeter radiation, found hydrogen cyanide in the coma. Hydrogen cyanide is a molecule made of hydrogen, carbon and nitrogen, and it is fairly common in comets. The amount of hydrogen cyanide was increasing steadily as the comet approached perihelion, going from about 1.5 times 10 to the power of 25 molecules per second in early September to about 4.5 times 10 to the power of 25 molecules per second a week later. That is about 2 kilograms of cyanide being released every second. It sounds like a lot, but remember, the coma is enormous, and the molecules spread out into a huge volume of space, so the concentration is actually very low. All of these observations paint a picture of a comet that is actively shedding material as it warms up. The ice on the surface is sublimating away, releasing gas and dust into space. Some of this material streams away to form the coma and tail, while other bits might fall back onto the comet's surface as it cools during the night side of each rotation. Scientists estimate that 3I/Atlas was losing a thin layer of material from its surface, maybe a millimeter or so of thickness over the whole time it spent near the Sun. That might not sound like much, but for an object that has been frozen solid for billions of years, even a millimeter is significant. It is like watching the first thin layer of snow melt off a car roof on a spring day. Underneath that thin layer is the ancient ice, the material that has been locked up since the comet first formed around another star. Now let's think about size. How big is 3I/Atlas? This is actually a tricky question to answer, and scientists are still debating it. The problem is that the comet is surrounded by that bright coma of dust and gas, which makes it hard to see the actual solid nucleus underneath. It is like trying to measure the size of a light bulb when it is turned on and glowing brightly. The glow makes it hard to see exactly where the solid part ends. From the Hubble Space Telescope images, scientists estimated that the nucleus, the solid, icy core, is somewhere between 440 meters and 5.5 kilometers across. 440 meters is about the length of 4 football fields laid end to end. 5.5 kilometers is about 3.5 miles, which is big enough that you could fit a small town on its surface if it were flat. The huge range in that estimate shows just how uncertain the measurement is. Some scientists, analyzing the brightness of the comet and the amount of light it reflects, think the nucleus might be even bigger, maybe up to 20 kilometers or so across. That would make it truly massive for a comet, bigger than almost any comet we have seen in our solar system. If 3I/Atlas really is that large, it would raise interesting questions. How did such a large object avoid being discovered until it was relatively close to us? Why is it so much bigger than the previous interstellar visitors? The previous 2 interstellar objects were much smaller. 1I/Oumuamua, the first interstellar visitor we ever confirmed, was probably only a few hundred meters long and shaped somewhat like a cigar or maybe a flat pancake. We never got a clear picture of its shape because it was so small and moving so fast by the time we noticed it. 2I/Borisov, the second interstellar comet, had a nucleus estimated at around 0.5 kilometer to 1 kilometer across, much smaller than 3I/Atlas might be. If 3I/Atlas is truly 10 or 20 kilometers wide, that makes it enormous by interstellar visitor standards. Some scientists wonder if we've been lucky to find something so big, or if objects like this are actually more common than we thought. Maybe smaller interstellar objects pass through all the time, but we miss them because they are too faint for our telescopes to spot. 3I/Atlas might be bright enough and big enough that we finally managed to see one of these travellers while it was still far away. The shape of 3I/Atlas is another mystery. Is it round like a ball, lumpy like a potato, elongated like a cucumber? The 16-hour rotation period gives us a hint. If the comet were a perfect sphere, it would not matter how it was spinning because it would look the same from every angle. But the brightness changes during each rotation suggest that the comet is not perfectly round. It probably has an irregular shape, more lumpy or elongated, so that when different parts face us during its spin, we see different amounts of surface area reflecting sunlight. Imagine holding a potato and spinning it slowly in front of a lamp. Sometimes the widest part faces the light, and the potato looks bright. Other times, a narrower end faces the light, and it looks dimmer. The brightness would change in a pattern matching how fast you spin the potato. That is essentially what 3I/Atlas is doing, except it is spinning in the vacuum of space with the sun as the lamp. The exact shape matters for understanding how the comet sheds dust. If one side is much bigger or bumpier than the other, that side might release more dust when it faces the sun. This would create even more variation in the dust release rate, adding another layer to those perfect beats we talked about earlier. Unfortunately, 3I/Atlas is too far away for even our best telescopes to see its actual shape directly. The coma is too bright, and the nucleus is too small. Scientists have to infer the shape from how the brightness changes, which is a bit like trying to figure out what an object looks like by watching its shadow move across a wall. Let's talk about speed again, because the speed of 3I/Atlas is one of the most remarkable things about it. When the comet entered the solar system from interstellar space, it was moving at 58 kilometers per second relative to the Sun, which is about 36 miles per second. That is the comet's hyperbolic excess velocity, a term scientists use to describe how fast an object is moving once you subtract out the influence of the sun's gravity. To put that in perspective, the fastest human-made spacecraft, the Parker Solar Probe, has reached speeds of about 120 kilometers per second during its closest approaches to the sun, but that is only because the sun's enormous gravity pulls it so fast. Out in interstellar space, far from any stars, Parker Solar Probe would slow down to much more modest speeds. 3I/Atlas, on the other hand, will leave the solar system moving at the same 58 kilometers per second it had when it arrived, because that is its natural speed through the galaxy. 3I/Atlas is moving faster than the previous interstellar objects. 1I/Oumuamua had an excess velocity of about 26 kilometers per second, and 2I/Borisov was moving at about 32 kilometers per second. 3I/Atlas is almost twice as fast as Oumuamua. This high speed is part of what allowed scientists to confirm so quickly that it came from beyond our solar system. Nothing born here could move that fast without getting a gravity boost from passing close to a planet, and 3I/Atlas did not come close enough to any planet to get such a boost. The comet's trajectory is described by something called orbital eccentricity, a number that tells you how stretched out or how circular an orbit is. Circles have an eccentricity of 0. Ellipses, which are like stretched circles, have eccentricities between 0 and 1. Hyperbolas, which are open curves that never loop back, have eccentricities greater than 1. 3I/Atlas has an orbital eccentricity of 6.14, one of the highest ever measured for any object in our solar system. This extremely high eccentricity means the comet's path is almost a straight line through the solar system, just barely curved by the sun's gravity. By mid-December 2025, 3I/Atlas will be about 170 million miles from Earth, roughly twice the distance from Earth to the Sun. That will be its closest approach to our planet. Even at that distance, it will be much too faint for most people to see without a decent telescope. Serious amateur astronomers with good equipment can still spot it as a fuzzy grey smudge moving slowly against the background stars, but it will not be visible to the naked eye. As we move through late 2025 and into 2026, 3I/Atlas will continue moving away from the Sun, getting fainter and fainter as it goes. By spring of 2026, it will pass the orbit of Jupiter, and by then it will be so dim that only large professional telescopes will be able to track it. Eventually, after a few more years, it will fade beyond detection entirely, too distant and too faint for even the most powerful telescopes on Earth or in space. And then, like a ship disappearing over the horizon, 3I/Atlas will be gone, back into the depths of interstellar space. Where will it go? Scientists have calculated its future path through the galaxy. 3I/Atlas will drift away from our solar system, heading out into the space between stars once again. It will pass through regions where stars are sparse, drifting for millions of years without coming close to anything. Eventually, billions of years from now, it might pass near another star system, maybe even fall into that system like it fell into ours. If that happens, and if there are intelligent beings in that system with telescopes, they might discover 3I/Atlas and wonder where it came from, just as we are doing now. But here is the beautiful part. By the time 3I/Atlas reaches another star, our sun will still be shining, and Earth will still be here, though it will be a very different place. The comet is a time traveler of sorts, carrying ancient ice across the galaxy, connecting star systems separated by vast distances and immense stretches of time. Now let's step back and think about what we have learned from watching 3I/Atlas shed its dust in perfect beats. The 16-hour rotation period tells us that the comet is spinning relatively slowly compared to many other comets. Some comets spin once every few hours. 3I/Atlas takes more than twice as long. This slow spin might mean the comet is fairly large, because larger objects tend to spin more slowly. It might also mean the comet has not been hit by anything in a long time. Collisions can change how fast an object spins, and if 3I/Atlas has been drifting through empty interstellar space for billions of years, it probably has not collided with anything since it left its home system. The rhythmic dust shedding shows us how heat from the sun interacts with the icy surface. During each 16-hour rotation, a fresh patch of surface comes into sunlight and starts to warm up. The warming causes sublimation, which releases gas and dust. As that patch rotates back into shadow, it cools down, and the sublimation slows or stops. This cycle repeats over and over, creating those pulses of dust we see. The fact that we can measure this pattern so clearly shows how carefully scientists are watching this visitor. The reddish colour of the dust tells us that the comet's surface is rich in organic molecules, the building blocks of chemistry that can eventually lead to life. These organics formed billions of years ago in the disk of gas and dust around the comet's parent star. Cosmic rays altered them during the long journey through interstellar space, breaking some molecules apart and creating new ones. The result is a complex mixture of carbon-based compounds, similar in some ways to what we find on comets in our own solar system, but with differences that reflect the unique history of 3I/Atlas. The high ratio of carbon dioxide to water is one of the most important discoveries. It tells us that the comet formed far from its parent star. in a cold region where carbon dioxide could freeze easily. This is consistent with the idea that 3I/Atlas came from something like an Oort cloud around another star. The Oort cloud in our solar system is thought to contain trillions of icy objects, the leftovers from planet formation that got flung to the outer edges of the solar system. Every star with planets probably has a similar cloud of debris, and occasionally objects from these clouds get tossed out into the galaxy to become interstellar wanderers. The metals in the comet, like nickel, tell us about the dust grains that were mixed into the ice. These grains likely formed in the atmospheres of older stars that existed before the comet's parent star. When those old stars died, they released their material into space, enriching the gas clouds that would eventually form new stars and planetary systems. The nickel in 3I/Atlas is ancient stardust, forged in the core of a star billions of years ago, then incorporated into the comet when it formed. One of the most exciting things about studying 3I/Atlas is that it allows us to learn about another planetary system without actually going there. We can never visit the star where this comet was born. That star is somewhere in the Milky Way galaxy, but we do not know which one it is. There are hundreds of billions of stars in our galaxy, and tracing 3I/Atlas back to its exact birthplace is impossible with current technology. The comet has been travelling for so long that its parent star has moved far away from where it was billions of years ago. Stars orbit around the centre of the galaxy, just like planets orbit around stars, but on much longer timescales. Even though we cannot visit that distant system, 3I/Atlas brings us a sample of it. Every molecule in its ice, every grain of dust in its coma came from that other system. By studying these materials, we learn what conditions were like around that distant star. We learn what kinds of ices formed there, what kinds of chemistry happened, what kinds of materials were available when planets might have been forming. In a way, 3I/Atlas is like a messenger from across the galaxy, carrying information about places we will never see. This idea of learning about other worlds through interstellar visitors is not new, but it is still incredibly exciting. Before 2017, we knew that interstellar objects must exist. The math told us that every star with planets should occasionally fling objects out into the galaxy, and those objects should drift through space until they encounter other star systems. But seeing one is different from knowing they must exist. 3I/Atlas is physical evidence that other planetary systems are out there. Systems with their own collections of comets and asteroids, systems where the same basic processes of planet formation that shaped our solar system are also at work. Let's take a moment to talk about the other two interstellar visitors, because comparing them helps us understand what is typical and what is unusual. 1I/Oumuamua was discovered in October of 2017 by the Pan-STARRS telescope in Hawaii. The name Oumuamua means scout or messenger in Hawaiian, chosen to honour the heritage of the place where it was first spotted. Oumuamua was strange from the beginning. It did not have a visible coma, so at first astronomers thought it might be an asteroid rather than a comet. But as they watched it move away from the sun, they noticed it was accelerating slightly more than gravity alone could explain. This extra push suggested that some kind of outgassing was happening, even though they could not see a coma. The debate about Oumuamua continues to this day. Some scientists think it is a comet made of nitrogen ice, which would sublimate without creating much visible dust. Others suggest it could be a fragment of a planet that got shattered in its home system. A few scientists, including some well-known researchers, have even suggested it might be an artificial object, a piece of technology from another civilization. Most astronomers think the natural explanations are more likely, but the mystery of Oumuamua shows how much we still have to learn about interstellar objects. 2I/Borisov was discovered in August 2019 by an amateur astronomer named Gennady Borisov using a telescope he built himself. Borisov looked much more like a traditional comet, with a bright coma and a visible tail. Its chemical composition, studied by multiple telescopes around the world, turned out to be fairly similar to comets from our own solar system, though with some interesting differences. For example, Borisov had very high levels of carbon monoxide, higher than most solar system comets. This suggested it formed in an especially cold region of its home system, even colder than where most of our own comets formed. In March 2020, astronomers watching Borisov saw something dramatic. The comet started to break apart, splitting into at least two pieces. This fragmentation is not uncommon for comets. The stress of warming up as they approach the Sun, combined with the forces from outgassing, can cause weaker parts of a comet to crack and break off. But seeing it happen to an interstellar comet was fascinating, because it gave scientists a chance to study the interior structure of an object from another star system. When a comet breaks apart, fresh material from inside gets exposed to sunlight for the first time, releasing a burst of gas and dust that telescopes can analyze. Comparing 3I/Atlas to its two predecessors reveals some interesting patterns. All three objects came from different directions in the sky, suggesting they originated from different parts of the galaxy. Oumuamua came from the direction of the star Vega, Borisov came from near the constellation Cassiopeia, and 3I/Atlas came from near Sagittarius. This tells us that interstellar objects are not streaming toward us from any particular direction. They are scattered throughout the galaxy, moving in all sorts of different paths. The sizes are different too. Oumuamua was probably the smallest, maybe 200 to 400 meters long. Borisov was intermediate, around half a kilometer to a kilometer across. 3I/Atlas might be the largest, possibly several kilometers wide. Does this mean larger interstellar objects are more common? Not necessarily. It might just mean that larger objects are easier to spot. A bigger comet reflects more sunlight and produces a bigger, brighter coma, making it visible from farther away. Smaller objects have to come much closer to the Sun before we can detect them, and by then they are moving so fast that we only get a brief window to study them before they vanish again. The chemical compositions show variety too. Oumuamua remains mysterious because we never got good spectra showing what it's made of. Borisov showed high carbon monoxide and seemed fairly similar to some of our own comets. 3I/Atlas shows exceptionally high carbon dioxide and lower water content. This variety tells us that conditions around other stars can be quite different from conditions in our solar system. Some planetary systems might be richer in certain molecules than others, depending on the exact mix of elements available when the system formed, how far from the star different materials condensed, and what happened during the chaotic period of planet formation, when objects were colliding and mixing. One question scientists are eager to answer is how common interstellar visitors really are. If we can spot 3 of them in just 8 years, does that mean there are many more out there that we are missing? Almost certainly yes. Small, dark objects that do not develop bright comas are nearly impossible to detect unless they pass very close to Earth. Even large objects can slip by unnoticed if they stay far from the Sun, where they remain cold and inactive. Telescopes are getting better at finding these visitors. The Atlas system that discovered 3I/Atlas is specifically designed to scan the entire visible sky every couple of nights, looking for anything that moves or changes. Other survey telescopes like the Vera C. Rubin Observatory being completed in Chile will be even more powerful. Rubin Observatory will photograph the entire southern sky every few nights, going deep enough to spot objects that are much fainter than what current surveys can detect. When Rubin comes fully online, scientists expect to discover many more interstellar objects. Some estimates suggest we might find several per year once all our new telescopes are working. Finding more interstellar visitors will help scientists understand how typical our solar system is compared to others. Every interstellar comet carries information about its birth system, encoded in its chemistry, its size, its structure, and its behavior. By studying a large sample of these visitors, we can start to answer big questions. Are most planetary systems similar to ours, with rocky planets close to the star and giant planets farther out? Or is our arrangement unusual? Are comets around other stars mostly made of the same materials as ours? Or do they show exotic chemistries we have never seen? How often do planetary systems eject objects into interstellar space? And what does that tell us about how planets form and migrate? These are not just academic questions. They touch on one of the deepest questions humans have ever asked. Are we alone in the universe? Understanding how common different types of planetary systems are helps us estimate how many might have planets suitable for life. If we find that most interstellar comets are rich in water and organic molecules, that suggests the ingredients for life are widespread in the galaxy. If we find that some systems produce very different kinds of comets with exotic chemistries, that tells us conditions can vary widely from star to star, which might affect how often life emerges. 3I/Atlas, with its rhythmic dust shedding, its ancient ice, and its long journey across the galaxy, is one piece of this much larger puzzle. Every observation scientists make, every spectrum they capture, every measurement of brightness or rotation period adds another tiny bit of information to our growing understanding of how planetary systems work throughout the galaxy. Now let's shift our attention forward. What happens to 3I/Atlas now? As we have discussed, it is already moving away from the Sun, heading back out into the outer solar system. By early 2026, it will be beyond the orbit of Jupiter, and the Sun's heat will no longer be strong enough to sublimate much ice from its surface. The coma will fade, the tail will disappear, the comet will return to its frozen state, becoming once again a dark, cold chunk of ice drifting through space. But here is something wonderful to think about. Even though 3I/Atlas is leaving our solar system, it is not really gone. It exists. It is out there. As you read these words as you go about your day tomorrow and the next day and the day after that, 3I/Atlas is tumbling through space, moving farther from us with every passing second, but still real, still spinning once every 16 hours, still carrying its cargo of ancient ice and dust. In 100 years, 3I/Atlas will be far beyond the orbit of Neptune, out where the sunlight is so faint it barely provides any warmth at all. The comet will be completely frozen again, its surface temperature dropping back to just a few dozen degrees above absolute zero. Any damage done by its brief warming during the summer and fall of 2025 will be preserved, frozen in place like a scar in ice. In 1,000 years, 3I/Atlas will be even farther away, approaching the distance where the sun's gravity becomes so weak it barely has any effect. The comet will still be moving at its steady 58 kilometers per second, coasting through the dark. By then, the telescopes we use to study it will be historical relics, and the scientists who observed it will be long gone. But their data will remain, carefully archived, available to future generations who will look back at our first detailed studies of interstellar visitors and see them as the beginning of a new era in astronomy. In 1,000,000 years, 3I/Atlas will have travelled about 50 trillion kilometres from our Sun, putting it roughly halfway to the nearest star. The space between stars is so vast that even travelling at tens of kilometres per second, it takes millions of years to cross from one star system to another. During this long voyage, 3I/Atlas will be utterly alone. No planets nearby, no moons, no other comets or asteroids. Just the comet, spinning slowly in the infinite dark, with only the distant light of stars providing any illumination. In 1,000,000,000 years, 3I/Atlas might pass near another star. If it does, and if that star has planets, the comet will fall into that system just as it fell into ours. It will warm up again, its ice will sublimate, and it will develop a coma and tail. If there are astronomers in that distant system, they will discover 3I/Atlas and study it, learning about the galaxy from a traveller that once passed through our own solar system. In a sense, 3I/Atlas will carry a memory of us into the future, a memory written in the patterns of dust and gas it leaves behind, in the exact ratio of carbon dioxide to water, in the trace metals and organic molecules that scientists in that future system will measure. They will not know the comet visited Earth. They will not know we saw it and wondered about it. But they will study the same ice we studied, and perhaps they will wonder, just as we do, about the long journey this ancient object has taken across the galaxy. Before we move on to explore related objects in the space community, let's take stock of the key things we have learned about 3I/Atlas. First, it is an interstellar comet, only the third such object we've ever confirmed. It came from beyond our solar system, from the space between stars, carrying ice and dust that formed billions of years ago around a different star. Second, 3I/Atlas sheds dust in a regular rhythm tied to its 16-hour rotation period. As it spins, different parts of its surface face the sun and warm up, causing ice to sublimate and release dust and gas. This creates a pattern, a beat, that astronomers can measure and study. Third, the comet has an unusual chemical composition compared to most comets we know, with much more carbon dioxide than water. This tells us it formed far from its parent star in a very cold region, and it gives us clues about conditions in that distant planetary system billions of years ago. These three facts alone make 3I/Atlas remarkable. But beyond the facts, there is something else, something harder to put into words. 3I/Atlas represents connection. It connects our solar system to another system across vast distances of space and time. It connects the past, when it formed, to the present, when we see it, to the future, when it will visit other stars. It connects different branches of science, bringing together astronomers who study orbits with chemists, who analyze molecules with physicists, who model how heat moves through ice. And it connects all of us who have looked up at the night sky and wondered what else is out there, beyond the reach of our eyes, waiting to be discovered. Now, let's turn our attention to other fascinating objects that are being discussed in the space community right now, objects that relate to interstellar visitors, comets, and the ongoing exploration of our cosmic neighbourhood. When astronomers first spotted 1I/Oumuamua racing through our solar system in October 2017, nobody quite knew what to make of it. The Pan-STARRS telescope in Hawaii, scanning the sky for asteroids that might pose a threat to Earth, picked up a faint dot moving against the background stars. At first it seemed like just another asteroid, the kind that astronomers discover every week. But as more observations came in over the following days, something strange became clear. This object was moving on a path that would carry it completely out of the solar system. It was not orbiting the sun. It was just passing through. The discovery set off a scramble. Telescopes around the world turned toward Oumuamua to gather as much data as possible before it sped away forever. Scientists had never seen anything like it before. Here was an object from another star system, something that had travelled through interstellar space for millions or billions of years. Now briefly visiting our solar neighbourhood, it was like a ship from a distant land sailing past your shore just once. If you did not study it carefully while it was visible, you would never get another chance. What made Oumuamua truly fascinating was how strange it looked in the data. Most asteroids and comets tumble through space in somewhat predictable ways. They reflect sunlight fairly steadily, maybe brightening or dimming a little as they rotate, but usually in ways that make sense given their shape and how fast they spin. Oumuamua was different. As astronomers watched it over several days, they saw its brightness change dramatically, varying by as much as 10 times between its brightest and dimmest points. This huge variation happened on a regular cycle, repeating every 7 to 8 hours. That enormous brightness variation suggested something unusual about Oumuamua's shape. If it were a simple sphere or a chunky potato-shaped rock, the brightness would not change that much. The data suggested Oumuamua was highly elongated, shaped somewhat like a cigar or maybe a flat disc or pancake. Imagine a long, thin object tumbling end over end. When the long side faces you, it reflects a lot of light and looks bright. When the narrow end points toward you, it reflects much less light and looks dim. The changing brightness follows the tumbling motion, creating that dramatic variation astronomers measured. Scientists estimated that Oumuamua might be about 400 meters long and only about 40 meters wide, making it 10 times longer than it is wide. That is an extremely unusual shape for a natural object. Most asteroids and comets are not that elongated. They tend to be lumpy and irregular, but roughly as wide as they are long. Finding something shaped like Oumuamua made scientists wonder what kind of processes could create such an extreme shape. Maybe it was a fragment from a larger body that got shattered in a collision. Maybe it formed that way naturally during the planet formation period in its home system. Maybe tidal forces from passing too close to a star or planet stretched it out. Nobody knows for sure. The mystery deepened when astronomers noticed that Oumuamua was accelerating slightly as it moved away from the Sun. This extra acceleration could not be explained by gravity alone. Something was giving Oumuamua a tiny push in addition to the gravitational forces acting on it. When comets accelerate unexpectedly, the usual explanation is outgassing. As the Sun warms a comet's icy surface, the ice turns to gas and jets away from the surface, creating a small rocket effect that can speed up or slow down the comet, depending on which direction the jets are pointing. But Oumuamua did not have a visible coma or tail, the telltale signs of outgassing. Telescopes looked carefully but could not detect any dust or gas around it. This led to a puzzle. How could Oumuamua be outgassing without producing a visible coma? Several ideas emerged. One possibility is that Oumuamua is made of unusual ice that does not produce much dust when it sublimates. Nitrogen ice, for example, turns directly to gas without dragging along much dust, so a nitrogen iceberg might outgas invisibly. Molecular hydrogen ice is another possibility, releasing pure hydrogen gas that is very hard to detect. Another idea is that Oumuamua is not a comet at all, but rather a rocky asteroid, and the acceleration comes from some other effect. One team of scientists suggested that thermal radiation pressure might explain it. When sunlight heats one side of a small elongated object, that side radiates heat back into space as infrared light. Photons of light carry momentum, so when the object radiates photons preferentially from one side, it creates a tiny push in the opposite direction like a very weak rocket. For an object with Oumuamua's unusual shape, this effect might be strong enough to explain the observed acceleration. A few scientists, most notably Professor Avi Loeb from Harvard University, have proposed a more exotic explanation. Loeb suggests that Oumuamua might be an artificial object, a piece of technology created by another civilization. He has compared it to a light sail, a thin reflective sheet that could be pushed through space by the pressure of starlight. If Oumuamua were a thin, flat object rather than a cigar-shaped one, it might be pushed by sunlight in a way that explains both its unusual acceleration and its extreme brightness variations. Loeb argues that scientists should seriously consider this possibility rather than dismissing it out of hand. Most astronomers are skeptical of the artificial object idea. They point out that natural explanations, while not completely understood, seem more likely given what we know about planetary systems and the objects they produce. The galaxy is full of stars with planets, and every planetary system probably ejects billions of comets and asteroids into interstellar space over its lifetime. Finding one of these natural interstellar wanderers seems far more probable than finding a piece of alien technology, especially since we have no other evidence that technological civilizations are common in the galaxy. But the debate is healthy. Science advances when people ask difficult questions and challenge each other to come up with better explanations. Oumuamua remains mysterious precisely because we could not study it in enough detail before it left. It was moving so fast and was discovered so late in its pass through the solar system that we only had a few weeks to observe it. By the time scientists fully understood what they were looking at, Oumuamua was already speeding away, getting fainter every day. Within a few months, it faded beyond detection, disappearing into the darkness between stars. The mystery of Oumuamua teaches us an important lesson. When an interstellar object passes through, we need to study it as quickly and thoroughly as possible. We need to be ready with our best instruments, our fastest response times, and our most creative thinking. This lesson shaped how scientists approach the next interstellar visitor, 2I/Borisov, and how they are approaching 3I/Atlas now. Today, Oumuamua is gone, somewhere out in the vast space beyond Neptune, continuing its journey through the galaxy. It is moving at about 26 kilometers per second relative to the Sun, heading in the general direction of the constellation Pegasus. In about 20,000 years, it will pass near a star called Ross 248, a small red dwarf about 10 light-years from our Sun. By then, Oumuamua will have been coasting through the dark for 200 centuries, unchanged and unchanging, a silent traveller carrying secrets we may never fully understand. On August 30th, 2019, an amateur astronomer in Crimea named Gennady Borisov was scanning the night sky with a telescope he had built with his own hands. Borisov is passionate about finding comets, and he spends many clear nights searching for faint, fuzzy objects that might be new discoveries. On that particular night, his telescope picked up something interesting. A small, fuzzy patch of light that was not on his star charts. He took careful note of its position and photographed it to document the discovery. Borisov reported his finding to the Minor Planet Center, an organization that tracks comets and asteroids for the worldwide astronomy community. Other astronomers immediately started taking their own observations to confirm the discovery and calculate the object's orbit. Within just a few days, it became clear that this was something special. The object, temporarily designated C/2019 Q4, was moving on a strongly hyperbolic path. It was not bound to the Sun. It was an interstellar comet, only the second object from beyond our solar system ever confirmed. The discovery was thrilling for several reasons. First, unlike Oumuamua, which was discovered on its way out of the solar system, 2I/Borisov was discovered while it was still approaching the Sun. This meant astronomers would have months to study it before it made its closest approach and then departed. Second, Borisov looked like a proper comet. It had a bright coma and a tail, making it much easier to study than the mysterious Oumuamua. Scientists could take spectra of the gas and dust, measure how much material was being released, and watch how the comet behaved as it got closer to the Sun. The Minor Planet Center officially renamed the comet 2I/Borisov in recognition of its discoverer and its interstellar origin. The number 2I means it was the second confirmed interstellar object, following 1I/Oumuamua. Astronomers around the world immediately started planning observing campaigns. Telescopes in Chile, Hawaii, the Canary Islands, and many other locations turned toward the comet. Space telescopes, including Hubble and the XMM Newton X-ray telescope, also observed it. Even the ALMA radio telescope array in Chile, normally used to study distant galaxies and planet-forming disks, took time to look at Borisov. As observations accumulated through the fall of 2019, a picture emerged of what Borisov was like. The nucleus, the solid icy core, was estimated to be somewhere between 200 meters and 1 kilometer across. It was shedding gas and dust actively, losing somewhere between 30 and 100 kilograms of material per second as it warmed up. The coma extended for thousands of kilometers around the nucleus, and the tail stretched for millions of kilometers behind the comet as it moved through space. Chemically, Borisov was fascinating. Spectra showed it contained water vapor, carbon monoxide, carbon dioxide, and cyanide, all common ingredients in comets from our own solar system. But the ratio of carbon monoxide to water was unusually high, about 50%, meaning there was roughly 1 carbon monoxide molecule for every 2 water molecules. Most comets in our solar system have much less carbon monoxide, typically only a few percent compared to water. This high ratio suggested that Borisov formed in a very cold environment, even colder than the regions where most of our own comets formed. Scientists compare chemical compositions by looking at what they call depletion factors or enhancement factors. These numbers tell you whether a particular molecule is more or less common in one comet compared to another. Borisov's high carbon monoxide content placed it at the extreme end of what we see in solar system comets, similar to the coldest and most pristine comets from the distant Oort cloud. This made sense. If Borisov formed in the outer reaches of its home planetary system, in conditions similar to our Oort cloud, you would expect it to preserve a lot of carbon monoxide, which can only stay frozen at very low temperatures. The dust in Borisov's coma also provided clues. Observations from ALMA showed that the dust grains were larger than expected, mostly millimeter-sized pebbles rather than fine powder. This was surprising because the pressure of sunlight and the drag from gas escaping the comet should push the smallest dust grains away fastest, creating a coma dominated by fine particles. The presence of larger grains suggested that something about Borisov's outgassing process favoured releasing bigger chunks of material, Or perhaps the comet's surface had a layer of larger pebbles that got lifted off as the ice beneath them sublimated. Polarization measurements, which look at how light waves align when they reflect off dust grains, showed that Borisov's dust was fluffy and porous, similar to the dust from solar system comets. This suggested that the process of forming dust grains around other stars might be similar to what happens in our own solar system. Tiny particles stick together over millions of years, building up larger, fluffy aggregates that resemble soot or very fine snow. One of the most exciting observations came from X-ray telescopes. When solar wind particles, which are electrically charged, slam into the gas in a comet's coma, they can produce X-rays, a form of very high-energy light. The XMM Newton telescope detected faint X-rays coming from Borisov, confirming that the comet's coma was interacting with the solar wind. This was interesting because it showed that comets from other star systems behave the same way as our own comets when they encounter our sun's solar wind. The basic physics is the same, regardless of where the comet was born. As Borisov approached its closest point to the sun, astronomers watched carefully for any changes. On December 8, 2019, the comet reached perihelion at a distance of about 2 astronomical units, meaning it was about twice as far from the sun as Earth is. Even at that relatively safe distance, the sun's heat was enough to cause significant sublimation. The comet's brightness increased, and its coma and tail grew longer. Then, in mid-March 2020, something dramatic happened. Telescopes in Chile and Hawaii noticed that Borisov's brightness suddenly increased. The comet became noticeably brighter over just a few days, and high-resolution images from Hubble showed that the nucleus had split into at least 2 pieces. The comet was fragmenting, breaking apart under the stress of warming and outgassing. Cometary fragmentation is not rare. Many comets in our solar system have broken apart over the years. Sometimes a comet splits into 2 or 3 large pieces that continue moving along similar paths. Other times, a comet completely disintegrates into a cloud of dust and small fragments that quickly spread out and dissipate. Borisov did not completely disintegrate. It split into a few pieces that stayed relatively close together, suggesting that the nucleus had weak spots or cracks where stress built up until part of the comet broke away. Watching Borisov fragment was scientifically valuable because fragmentation events expose fresh material from inside the comet. The outer layers of a comet can become altered by cosmic rays and weathering during the long journey through interstellar space, but the interior should be more pristine, less changed since the comet first formed. When Borisov broke apart, that fresh interior material was suddenly exposed to sunlight, releasing a burst of gas and dust that telescopes could analyze. Scientists looked carefully at the spectra during and after the fragmentation event to see if they could detect any differences from the material being released before the breakup. The fragmentation also confirmed that Borisov was structurally weak, held together more by its own weak gravity than by any strong internal structure. This is typical of comets, which are often described as dirty snowballs or, more accurately, as piles of rubble loosely bound together. The ice and dust that make up a comet nucleus do not form a solid, strong rock. Instead, they create a fragile mixture that can break apart easily if disturbed. By May 2020, Borisov was moving away from the Sun again, heading back toward the outer solar system and eventually to interstellar space. As it moved outward and cooled down, the coma faded and the tail shortened. By mid-2020, the comet had become too faint for most telescopes to follow. The last detected observations came from some of the largest telescopes on Earth, capturing Borisov as a faint smudge getting dimmer and dimmer as it receded. Today, 2I/Borisov is somewhere beyond the orbit of Uranus, continuing its journey out of the solar system. It is moving at about 32 kilometers per second relative to the Sun, heading back into interstellar space. Unlike Oumuamua, Borisov will carry visible scars from its visit. The fragmentation event changed the comet's structure, and the months of active outgassing stripped away a thin layer of material from its surface. When Borisov eventually passes near another star billions of years from now, it will be slightly smaller and slightly different than when it arrived here, a record of its brief encounter with our Sun written into its very structure. The study of 2I/Borisov taught scientists many important lessons. First, it confirmed that interstellar comets can look and behave very much like comets from our own solar system. The basic chemistry is similar, the outgassing processes work the same way, and the structural properties are comparable. This suggests that the conditions under which comets form might be fairly similar around many different stars. The basic physics and chemistry of planet formation seem to produce similar outcomes in different systems, at least when it comes to the icy objects that get flung into interstellar space. Second, Borisov showed that having advance warning of an interstellar visitor makes a huge difference. Because it was discovered while approaching the Sun rather than leaving, scientists had time to plan carefully, schedule observations on the best telescopes, and coordinate campaigns involving multiple observatories. The data collected from Borisov far exceeds what was gathered from Oumuamua, simply because there was more time to work with. Third, the fragmentation event highlighted how valuable it can be to watch interstellar visitors closely over their entire passage through the solar system. Unexpected events like breakups or outbursts can provide unique scientific opportunities, but only if telescopes are watching when they happen. This has motivated astronomers to develop better systems for monitoring known interstellar objects continuously, rather than just taking a few snapshots and moving on. Finding 3 interstellar objects in 8 years has energized the astronomy community. If 3 have been spotted, how many more are passing through unnoticed? Estimates vary, but some scientists think there might be several interstellar objects within the orbit of Neptune at any given time. Most of these would be too small or too dark to detect with current telescopes, visible only if they happen to develop a bright coma like Borisov or 3I/Atlas. Several new telescope projects are specifically designed to improve our ability to find and track objects moving through the solar system. The Vera C. Rubin Observatory, scheduled to begin full operation soon, will be a game changer. This telescope in Chile will photograph the entire visible southern sky every few nights, going deep enough to detect objects much fainter than what current surveys can see. Its camera, the largest digital camera ever built for astronomy, will capture 3 billion pixels in each image, enough to see incredible detail across huge swaths of sky. When Rubin Observatory starts its regular survey, scientists expect the number of known asteroids, comets, and other solar system objects to increase dramatically. Current catalogues list a few million objects. Rubin might discover tens of millions more. Hidden among all those discoveries, there should be more interstellar visitors. Some estimates suggest Rubin might find 1 or 2 interstellar objects per year, maybe more. Each discovery will add to our growing understanding of what exists in the space between stars. The Nancy Grace Roman Space Telescope, set to launch later this decade, will also contribute to the search. Roman is a space telescope designed primarily to study dark energy and exoplanets, but its wide field of view and sensitive detectors make it excellent for discovering transient and moving objects. Unlike ground-based telescopes, Roman will not be affected by weather, atmosphere, or daylight, allowing it to observe 24 hours a day. Its position in space will give it views of parts of the sky that ground telescopes cannot see. Another exciting project is the Comet Interceptor mission, being developed by the European Space Agency. This mission will work differently from traditional space missions. Instead of launching toward a specific target, Comet Interceptor will launch to a special point in space called Lagrange Point 2, or L2, where it will wait for a suitable target to appear. L2 is a location about 1.5 million kilometers from Earth, directly opposite the Sun, where the gravitational pulls of the Earth and Sun balance out. A spacecraft at L2 needs very little fuel to maintain its position, making it an ideal parking spot. Comet Interceptor will wait at L2 until astronomers discover a really interesting comet heading into the inner solar system. This could be a pristine comet from the Oort cloud making its first visit near the Sun, or it could be an interstellar comet like 3I/Atlas. Once a target is selected, Comet Interceptor will leave its parking spot and fly to meet the comet, studying it up close with cameras and scientific instruments. The mission even includes 3 separate spacecraft that will split apart before the encounter, allowing them to photograph the comet from multiple angles simultaneously. If an interstellar comet is discovered with enough advance warning, Comet Interceptor could potentially reach it and provide humanity's first close-up look at an object from another star system. Imagine cameras capturing detailed pictures of the nucleus, showing the shape, the surface features, the exact locations where jets of gas and dust are erupting. Imagine instruments measuring the composition of the ice and dust directly, rather than inferring it from spectra taken from millions of kilometers away. Such a mission would revolutionize our understanding of interstellar objects and what they can teach us about other planetary systems. The hunt for interstellar visitors is not just about finding the objects themselves. It is also about understanding where they come from and how common they are. Every star with planets probably creates a population of comets and asteroids during its planet formation period. Some fraction of these objects gets thrown out into interstellar space by gravitational interactions with the planets. The exact fraction depends on the architecture of the planetary system, how massive the planets are, where they are located, and how the system evolved over time. By studying how many interstellar objects pass through our solar system, astronomers can work backward to estimate how many such objects exist in the galaxy as a whole. Early estimates based on the discovery rate of interstellar visitors suggest there might be trillions upon trillions of these objects drifting between the stars. If that is true, then interstellar space is not as empty as we once thought. It is populated with an enormous number of small bodies, the exiled remnants of planetary systems throughout the galaxy. While true interstellar objects like 3I/Atlas capture headlines, there is another group of fascinating objects that occupy a middle ground between comets and asteroids, between the inner and outer solar system. These objects are called centaurs, named after the mythical creatures that were half human and half horse, because centaurs exhibit characteristics of both asteroids and comets. Centaurs orbit the Sun in the region between Jupiter and Neptune. This is a transitional zone, neither the warm inner solar system where rocky planets orbit nor the cold outer reaches beyond Neptune where icy Kuiper Belt objects reside. Centaurs are thought to be objects that originated in the Kuiper Belt or scattered disk regions beyond Neptune but have been perturbed by gravitational interactions, causing their orbits to move inward. They are on unstable orbits, meaning they will not stay in the Centaur region forever. Eventually they will either get kicked out into more distant orbits, fall into the inner solar system to become short-period comets, or collide with a planet. What makes centaurs interesting is their diverse behavior. Some look like asteroids, showing no signs of activity or outgassing. Others have developed cometary features like comas and tails, even though they're still quite far from the Sun. This suggests that centaurs contain volatile materials like water ice, carbon dioxide ice, and other substances that can sublimate at relatively low temperatures. As a centaur moves inward and warms up gradually, these volatiles start to sublimate,